Hi, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for sleepy minds. Tonight we ride with Voyager 1, a small, tough spacecraft launched in 1977 to explore the outer planets and then keep going farther than any human-made object before it. We will see why Voyager 1 was built, how it flew past Jupiter and Saturn, what it learned from their moons and rings, and how it kept talking to Earth as the sun grew smaller behind it. We will drift with it to the edge of the sun's reach, cross into the space between the stars, and listen to the thin music of charged gas out there. Settle in, breathe easy, and let's begin the calm tour. But before you do that, take a moment to like the video and subscribe to the channel. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world. And thank you so much for being here. Voyager 1 began with a rare chance. In the late 1970s, the outer planets lined up in a way that let a single craft swing past one giant world and then use its gravity to bend and speed the path toward the next. This move is called a gravity assist. It is like stealing a tiny bit of a planet's motion and trading it for speed, saving fuel that a small craft can never carry. Engineers and scientists saw that window coming and designed a pair of nearly twin spacecraft, Voyager 1 and Voyager 2, to take it. Each was the size of a small car, but lighter, a body shaped like a box, a wide white dish for talking to Earth, 3 long booms holding instruments, and a bundle of power sources called RTGs at the end of a truss. An RTG, or radioisotope thermoelectric generator, is a steady nuclear battery that turns heat from a small amount of naturally decaying material into electricity. It has no moving parts, works in the dark, and keeps making power for decades, though a little less each year. That steady trickle of power, not sunlight, is what lets Voyager 1 live where the sun is a faint star. The main plan was simple to say and hard to do. Launch, check the craft in near-Earth space, cross the asteroid belt, race to Jupiter, map its clouds and moons, then use Jupiter's pull to reach Saturn, study its rings and Titan, and if the craft survived, bend the path upward out of the flat plane of the planets into the high dark. Board, a small computer system, tiny by today's standards, would choreograph thousands of steps, point the dish, aim the cameras, warm an instrument, time a picture, fire a thruster for a short puff, store data on a tape recorder, and beam it home through that bright dish. The faces of people at the control center showed quiet focus, because space is patient but unforgiving. A missed command can waste a precious chance that will never return. To keep the mission human, not just technical, the team placed a message on the craft. The Golden Record, a copper record plated in gold with sounds, music, languages, and pictures from Earth, plus a map that shows where the sun sits in the galaxy using the beats of special stars called pulsars. It was a simple hello to anyone or anything that might one day find a small machine drifting between suns. On September 5, 1977, after Voyager 2 had already gone, Voyager 1 rose on a Titan Centaur rocket from Cape Canaveral. The rocket's 2 bright steps did the heavy lifting. The last stage gave the final push. In a few minutes, the blue faded to black, and the spacecraft entered a path toward the outer dark. Controllers sent the first commands. The high-gain dish turned, the booms swung out, the slow spin steadied the craft, and the tiny heaters warmed what needed warmth. There was no cheering in space, only a steady stream of beeps and numbers that said, "I am alive, I hear you, and I am ready to begin." In the weeks after launch, Voyager 1 did the calm work that decides if a long journey can happen. It tested its eyes and ears. The 2 imaging cameras, one wide and one narrow, took pictures of the Earth-Moon pair from far enough away to see them together. A blue world, and a grey companion against black, a view no person could have then seen with their own eyes. Star trackers learned the sky like a sailor learning constellations, locking onto known patterns so the craft always knew which way it was pointing. The plasma instrument, which tastes the thin gas of charged particles around the sun, took first sips. The magnetometer boom swung out to feel the sun's magnetic field, and later the magnetic fields near planets. A cosmic ray detector began to count high-energy particles that shoot through space from distant events. A radio science system listened for changes in the signal caused by gas and dust, the way a voice sounds different when it passes through fog. Each instrument did a small job, and together they formed a team that could describe not just what Voyager 1 saw in pictures, but what it flew through and what it felt. Talking to Earth needed its own careful plan. The spacecraft's big white dish is like a tight flashlight of radio waves. It must point at our planet to be heard. On Earth, giant antennas of the Deep Space Network in California, Spain, and Australia take turns listening as the Earth turns, so at least one ear always faces Voyager. Signals are very weak by the time they arrive, like heat from a match across an ocean, so the network uses clean electronics, big dishes, and long listening times to tease data from noise. A tape recorder on Voyager stores pictures and measurements when the craft is busy and Earth's ears are not pointed its way. Then it plays them back slowly, bit by bit. Power is tight. The RTGs make only a few hundred watts at launch, less than many kitchen appliances, and that amount shrinks a little each year. Heaters are small and chosen carefully. Some instruments share warmth through their structure. The craft sleeps parts of itself when not in use. Even the tape recorder is run with care to extend its life. Thrusters sip tiny squirts of fuel to adjust aim. Every gram and every watt count. Past the orbit of the Moon, past the region where Earth's magnetic field still shields travelers, the craft slid into the solar wind, a very thin stream of charged particles that rushes outward from the sun. It felt micrometeoroid dust as faint taps and listened to the changing pressure of the wind as the sun breathed stronger and weaker. Home shrank behind it to a point. Ahead lay the wide band of rock pieces called the asteroid belt, and far beyond, the bright giant Jupiter, waiting like a striped lantern in the dark. The asteroid belt is not a crowded field of spinning boulders, as movies sometimes show it. It is wide and mostly empty, with small bodies very far apart, dust in between, and only now and then a path crossing close by a known rock. Voyager 1 crossed it in quiet fashion, the way a ship crosses a gentle sea, but the team stayed ready. The cameras scanned to catch any object of interest. The dust detector counted tiny hits. The magnetometer tracked dips and swirls in the solar wind as the sun's mood changed. The flight team sent small course corrections called TCMS, short bursts of the thrusters that trimmed the path so that months later the craft would pass exactly where it needed to pass at Jupiter. That is the art of deep space flight. You throw a stone now to hit a leaf that will fall far away much later, and a tiny nudge today becomes a perfect alignment at the right hour. Months from now. As Jupiter grew from a bright point to a disk, and then to a striped world, the team shifted from cruise to encounter mode. Timelines were built like sheet music. Point here, shoot there, switch filters, steady, hold, hand off to the next instrument, then to the next. Jupiter's magnetosphere, the bubble carved in the solar wind by its strong magnetic field, is huge, so Voyager 1 felt the giant long before it reached the clouds. The sun's flow bent and slowed. Charged particles trapped by Jupiter's field grew more intense. Radio emissions from the planet's powerful auroras, which are lights at the poles caused by charged particles pouring into the atmosphere, hissed and sang in the radio data. The cameras began long runs, watching cloud belts move so wind speeds could be measured. The Great Red Spot, a storm larger than Earth, rolled in the frame like a slow wheel with smaller storms dotting its edge. Nearby, 4 bright moons, Io, Europa, Ganymede, and Callisto, showed themselves as small disks. These were the worlds Galileo had first seen with a simple telescope centuries ago, and they would soon become places with faces and stories. As the days to closest approach fell towards zero, the team trimmed the flyby path a last time to set up the next act, because the point where you pass the planet decides not only what you see, but where you will be thrown by gravity when the dance is done. For Voyager 1, the path would drop past Jupiter, thread the system of moons, and then set the craft on a line towards Saturn 2 years later. The risk was real. Jupiter's radiation belts can harm electronics, and the speeds involved leave no time to fix a late mistake. But the craft and team were ready. The cameras were clean, the tape recorder was healthy, the dish was locked on Earth. The giant waited, striped, banded, restless, and bright. The days around closest approach to Jupiter in early 1979 turned a distant point into a living world. Voyager 1's pictures showed clouds stacked in bands with dark belts and bright zones, small white storms called ovals sliding and merging, and the great red spot as a massive whirl with curled edges and little eddies like cream in coffee. Filters sensitive to different colors of light revealed high and low clouds. Some frames caught lightning flashes on the night side, proving that deep storms crackled with electricity the way tropical storms on Earth do. The magnetometer and plasma instruments mapped the invisible bubble around Jupiter, finding strong fields and fast flows that shook the solar wind far upstream. Then came a quiet surprise, a thin dusty ring around Jupiter, so faint that only careful backlit images revealed it. Before Voyager, only Saturn was known to have rings. The new ring said that dust from tiny impacts on small inner moons could hang on as a skirt around the giant. The greatest shock came from Io. As Voyager watched, the small sulfur-rich moon showed tall plumes rising above its edge, bright fountains of volcanic gas and ash blown by Io's thin air. No one had ever seen active volcanoes beyond Earth before. The heat source is simple to say and powerful. Io's orbit is pulled by Jupiter and tugged by the other big moons in a way that flexes the moon's inside and warms it, like bending a metal wire back and forth until it's hot. The result is a world that remakes its surface again and again, painting it in yellows and whites and blacks, from sulfur and fresh lava. Europa, next out, wore a smooth, bright shell of ice crisscrossed by darker lines, cracks and ridges that hinted at motion, and perhaps later work would suggest a deep ocean under that ice. Ganymede showed big, bright and dark patches and long grooves, like a moon that had been stretched and scarred. Callisto, farthest of the 4, showed ancient, battered terrain packed with craters, a record of long time. The instruments also found big changes in the charged particles near these moons. Io's volcanoes filled Jupiter's space with sulfur and oxygen ions. Europa and Ganymede sat in that flow and shaped it. Close passes past the moons were timed like heartbeats. Cameras snapped rapidly at set angles. The craft turned to keep targets in frame and then turned back to beam data home. Every picture had to ride the weak radio beam across many minutes to Earth, where big dishes listened in deep night. When the flyby was done, Jupiter's huge pull had paid for the next leg of the trip. Voyager 1 left the King of Planets at a different speed and angle than it had arrived, carrying new speed like a gift. In its wake, it left a changed view of the solar system. Planets were not just balls. They were families of weather, fields, rings, and worlds with their own lives. The cruise from Jupiter to Saturn took a little over a year and a half, a long glide through cold sunlight. On board, the pace eased, but the work did not stop. Instruments switched to survey mode to watch the solar wind recover from Jupiter's shock and to measure how charged particles drifted in the deep space between giants. The craft listened to radio waves from the Sun and from Jupiter behind it, studied the way dust thinned and thickened, and tightened its aim towards Saturn with 2 or 3 small course-trim bursts called TCMS. One was enough to move the arrival point thousands of kilometers a year later, so each burn was planned and checked with care. Engineers watched the health of the tape recorder, the thrusters, and the heaters because time in deep space eats machines in slow ways, tiny leaks, weak valves, and thermal cycles. They also planned the encounter timeline in detail. Saturn is wrapped in rings like no other planet, bright, wide, and structured. Its biggest moon, Titan, is large enough to hold a thick atmosphere. That haze would be a key target because seeing the surface was not possible. The plan was to dive behind Titan and sample the way its air bent and dimmed a radio beam from Earth, a trick called radio occultation that tells you what the air is made of and how thick it is. Doing that meant flying close to Titan at a set height and time, and that in turn meant choosing a path past Saturn that gave up the chance to keep going toward Uranus and Neptune. The choice was not made lightly, but the science case was strong. Titan is a world with air, and learning its secrets would be worth it. While the planners tuned that path, the imaging team began long runs of Saturn and its moons from far out, watching the ring system brighten and learning how often to shoot to catch motion in moons and spokes in the rings. Spokes are ghostly dark streaks that seem to glide across the rings. They are made by dust and electric charges and sunlight. The magnetometer team set ranges to feel Saturn's magnetic field bend the solar wind. Every group rehearsed for the busy days. On Earth, the Deep Space Network checked scheduling so that the biggest dishes would face Voyager 1 at the peak of the flood of data. By late 1980, the planet's soft yellow disk and thin shadows of rings began to show detail in the cameras. Small moons appeared at the ring's edge like beads. Bigger ones, Mimas with its big crater, Enceladus bright as fresh snow, Tethys, Dione, and Rhea showed surfaces marked in different ways. The stage was set for a close look at a system that had long glowed in small telescopes as a simple oval of planet and line of rings, now ready to open into a whole arch of places and patterns. In the first days of November 1980, Voyager 1 threaded the Saturn system and turned it from a pretty symbol into living physics. Up close, the rings were not a single band, but thousands of narrow lines with gaps, waves, braids, and wakes shaped by gravity and by tiny grains bumping, charging, and shadowing each other. The cameras, timed to the second, caught ringlets fading and brightening as sunlight hit them at new angles. Where a small moon tugged on ring particles, waves rolled through the ring like ripples on a pond. Where 2 little moons, now called shepherd moons, flanked a narrow ring, their pulls kept the ring thin and sharp, the way 2 hands can keep a ribbon from fraying. Backlit views showed fine dust as a soft glow. Frontlit views showed ice chips flashing. The magnetometer felt the planet's field sweep past. The plasma instrument tasted the thin gas and dust that drifted between rings and moons. The cameras swung to the small inner moons, Mimas with its giant crater that makes it look like an eye. Enceladus, bright and strangely smooth in patches, as if its surface had been renewed not long ago in geologic terms. Tethys and Dione with long cracks and cliffs. Rhea with craters and soft tones. Then came Titan, the biggest moon, larger than the planet Mercury. In every picture, Titan refused to show a surface. It wore a deep orange haze that hid everything below. That haze is made from nitrogen, methane, and sunlight, cooking those gases into complex smog. Voyager 1 used a radio beam from Earth and listened as the beam slid behind Titan's edge. The way the beam bent and dimmed told the team that Titan's air is mostly nitrogen, like Earth's, but much colder and thicker at the surface, with methane as a major minor gas. The temperatures were far too cold for liquid water at the ground, but methane could act a little like water does on Earth, freezing, melting, maybe raining in cycles over long time. The surface stayed hidden, yet the air itself was a world of interest. That pass behind Titan was precise. It bent Voyager 1's path up and out of the flat plane of the solar system, like a marble thrown off a spinning plate. That was planned. It meant Voyager 2 would be the one to continue outward to Uranus and Neptune, while Voyager 1 climbed into the dark above the planets, free of future encounters, and aimed toward the edge of the sun's reach. The ring pictures kept coming as the craft sped away, long, low sun angles that made waves and edges stand out as razor-sharp lines, faint rings outside the bright main band, hints of spokes drifting as dust charged by sunlight, and Saturn's field danced in patterns that we still study. When the last planned images were taken and the tape recorder played them back over the big dishes for many days, the team exhaled. Jupiter had given speed, Saturn had given beauty and a rich, thick-aired moon. The path ahead held only the slow slope to the boundary where the sun's wind ends. The starfield grows steady and cold, and the spacecraft's ears would become its main eyes. From here on, Voyager 1 would be a listener more than a photographer, a patient witness rather than a visitor, writing down what space itself feels like as the light of the sun fades to a small memory behind it. Long before Voyager 1 ever saw Jupiter, the team decided to send a small hello with it. They did not know if anyone would ever find the craft, but they liked the idea that a tiny message might drift between the stars, just in case. That message is the Golden Record. It is a copper record plated in gold to resist rust and weather in space. It is strapped to the side of the spacecraft under the big white dish. The record holds sounds and pictures from Earth. It has music from many places and times, drums, flutes, voices singing. It has the sound of wind, thunder, birds, a baby crying, a kiss, a heartbeat, and the waves of the sea. It has greetings spoken in dozens of languages. It has simple pictures that show how our bodies look, how we live, what our homes and tools are like, what our animals and plants look like, and where we live on a world with oceans and continents. The record also carries a map in a simple form. On the front are line drawings that explain how to play it and how to find where the sun is in the galaxy. They used special stars called pulsars. A pulsar is a dead star that spins and sends out a steady radio beat, like a lighthouse. Each pulsar has a unique beat rate. The cover marks the angle from our sun to many pulsars and writes each beat rate as a number in a very basic unit. If someone finds the record and can measure those same pulsars, they can match the drawing to the sky and learn where the sun is and when the record was launched. The record also shows the shape of our hydrogen atom and uses its spin flip time as a basic clock. That makes it possible to turn the numbers on the cover into seconds and meters. Everything is explained in the simplest shapes and counts because the makers could not assume anyone reading it would know our words. The pictures and sounds are stored as an analog groove, like a long wavy line. The player for it is not sent, so the cover also includes a small drawing of a needle and the speed at which to play the record. A small cartridge with the needle is bolted next to the disc, along with a block of metal that shows a tiny version of the first picture on the record. That first picture is simple on purpose, a circle and a straight line that lines up the player with the groove. The hope is that the finder can decode the rest by following that start. The record is not a time capsule for us. It is a chance for anyone later to learn a little of what we were like on the day we launched these small machines. If no one ever finds it, that is fine too. The act of sending a kind hello says something about us. The team tested the materials under heat and cold to be sure the pictures and sounds would not flake or fade fast. A gold layer helps keep it safe from space dust and harsh sunlight. They also chose the side of the craft that faces forward during the long cruise, so the dish and body help shield the record from tiny strikes. When you imagine Voyager 1 now, moving in deep dark where the sun is a bright star, you can picture that golden circle riding along, quiet and patient, carrying music, wind, rain, and human voices across a space so large that it makes our world feel small and dear. It is both a gift to chance and a note to our future selves that says, we were here, we listened, we learned, we cared enough to share. Voyager 1 is small, but it carries a full set of simple, tough tools that turn a silent flight into a steady stream of knowledge. 2 cameras share a mount. One is a narrow-angle camera for fine details, like the edge of a ring or a cloud top. The other is a wide-angle camera for big scenes, like a whole planet with moons nearby. Each camera can use filters to look at different colors, which helps tell high clouds from low clouds and ice from dust. Close with those is a photopolarimeter, which looks at how light is scattered and how it is polarized. Polarized light is light with its waves lined up in a certain way. How much it is lined up tells you about the size and shape of the tiny particles that bounce it. That helps us read what ring grains or haze in an air layer are like. A plasma instrument tastes the thin gas of charged particles, called plasma, that flows from the sun and fills the space around planets. It measures speed, density, and temperature of that flow. A low-energy charged particle detector counts and weighs particles with more punch, which tell us about how planets trap and move them. A cosmic ray detector counts very high-energy particles from far away, which grow more common far from the sun and change at boundaries in space. A magnetometer on a long boom feels magnetic fields, both the sun's field and the fields around planets. Magnetic fields guide charged particles and shape the bubbles, called magnetospheres, around giant worlds. A radio and plasma wave tool listens to the hiss and whistle of waves in the plasma. These are not sound waves through air. They are tiny shakes in the sea of charges. They tell us when shocks pass by or when a planet's auroras sing in radio. A radio science system uses the craft's own radio as a probe. When a planet's air passes between the craft and Earth, the signal bends and dims. By measuring that, we can learn the air's thickness and makeup. The same radio can be used to time how signals shift when gravity pulls them. That helps weigh a planet, or moon, or ring. There is also an infrared tool that reads the heat glow of clouds and surfaces. Heat at different colors tells you how warm a place is, and how gases like methane and ammonia move heat up or down in a planet's air. These tools work best as a team. A picture can show a bright patch on a ring. The polarimeter can say the grains there are tiny. The magnetometer can say a moon's pull made a wave that concentrated those grains. The plasma tool can say the sun's flow was calm or rough at that time. Together, that tells a clear story. On a long cruise, power and heat are always tight. The RTGs feed a bus that keeps the tools alive. Heaters warm parts that must not freeze. The body of the craft shares heat across struts and plates. Engineers choose which tools to warm and run and which to rest, like a cook who cannot boil every pot at once. A simple computer stores a timeline of commands that run each move, and a tape recorder keeps data until Earth can listen. When the cameras later shut down to save power, the fields and particles tools kept going. They do not need light. They feel the space itself and write notes on its moving sea. That is why Voyager 1 could keep learning long after the last picture. It could feel the sun's breath fade and the touch of the space between stars grow strong. Steering in deep space is like tossing a leaf into a river and asking it to touch a floating stick miles downstream. You do not fight the current, you use it. Gravity is the current. Planets pull, the sun pulls. To change where you will be next year, you give a small push now. Voyager 1 carries only a small tank of hydrazine. Hydrazine is a simple fuel that breaks apart on a catalyst to make hot gas. That gas shoots out of tiny nozzles and nudges the craft. Each nudge is brief and small. The art is when to nudge and how much. Navigation starts with sight. The craft's star tracker watches a set of bright stars and keeps the big dish aimed at Earth. For fine aim to a planet, the imaging team also takes pictures of the planet against background stars. By measuring how the planet shifts in the frame over days, they know the path error and can tell the nav team how to trim it. These pictures are called optical navigation, or OpNav. Every OpNav picture must be planned so that the planet and the right stars are in view. The dish must still point at Earth often to send the pictures home. That means the craft has to twist and untwist many times each day in the last weeks before a flyby. Each twist spends a little fuel, so the timeline balances fuel cost against the need to refine the aim. Back on Earth, the Deep Space Network also measures the craft's radio very carefully. Tiny shifts in the signal's pitch, called Doppler shifts, tell how fast the craft moves toward or away from us along the line of sight. A set of long-range antennas can also measure the craft's angle by how the signal hits them. Blending Doppler, angle, and OpNav pictures, the team sets up a burn called a trajectory correction maneuver, or TCM. The TCM might last only a few seconds. Yet that few seconds can move the closest approach point by thousands of kilometers, months later. The team will plan several TCMs on the way to a planet, but skip one if the aim stays good. The last trim often happens just a few weeks before closest pass. After that, the path is ballistic, which means it is set by gravity and small torques only. The last days are for pointing the cameras and instruments, not for pushing the ship. Then, during the flyby, gravity turns the ship's path like a stone in a sling. A gravity assist does two things at once. It bends the path and trades energy. If the craft passes in front of the planet, it gives up a little speed and falls inward toward the sun more. If it passes behind, it steals a tiny bit of the planet's motion and speeds up. Since the planets are huge and the craft is small, the planet does not notice. But the craft gains or loses a lot by its own measure. At Jupiter, passing in the right place sped Voyager 1 towards Saturn. At Saturn, passing by Titan in a set way bent the path up out of the plane of the planets. These moves were planned years ahead and checked daily in the last weeks. You can see why a missed command hurts. The river only makes that bend once. What makes it work is patience, careful math, clean radio tracking, and a craft that points where it is told, and puffs when it is told, then sits still and quiet for the next long glide. Jupiter looks calm at a glance, a striped ball with a big spot. Up close, it is busy everywhere. Voyager 1 watched bands of clouds slide past each other in lanes. Some lanes flow east, some west, so where they meet you get shear, which is a sideways pull. Shear makes storms. The cameras saw little white ovals that spun for months. Some merged like drops of cream and became larger. Others faded into the bands. The Great Red Spot itself is a giant storm, like a high-pressure system, with winds that circle at hundreds of kilometers per hour. Around its edge, small storms spin and peel off. The spot's color comes from chemicals in the upper air that sunlight cooks, a bit like the orange haze on Titan, but formed in different gases. On the night side, the cameras caught flashes in clouds. Those were lightning, proof of strong up and down motion inside storms, which means water and other vapors were moving heat and making charge. With filters, the team could look high and low. High clouds of ammonia ice show one way, deeper clouds of other ices, and droplets show another way. By watching how fast features moved in sequences of images, the team made wind maps. Those maps, plus the radio waves from auroras and the feel of the planet's field by the magnetometer, told a story in which a deep rotating body, a fast spin, and sunlight and heat from within all joined to keep weather alive all the time. Even the thin ring was tied into this deep engine because dust in the ring falls in slowly and lights up in places where small moons and fields stir it. The discovery of Io's volcanoes changed the way we saw moons. We used to think moons were dead, cold rocks. Now we knew that tides from a giant planet could need a small world warm. That taught us to look at other moons with fresh eyes. Europa's smooth, cracked shell said the inside might be warm enough to keep a deep ocean under ice. Ganymede's grooves said something pulled and stretched its crust. Callisto's old face said it had stayed cold and unchanged for a very long time. The magnetometer and plasma tools showed that all 4 large moons sit in a river of charged gas from Io's plumes. Jupiter's fast spin and strong field trap that gas and fling it round and round. Where those flows hit the moons, they change. Where they hit the planet's poles, they glow as strong auroras. Jupiter taught us that a planet is not a ball alone. It is a machine with belts and wheels, with fields that shape space, with moons that feed and drain it, with a weather layer that never rests, because heat rises from inside and sunlight stirs the top. The lesson reaches beyond Jupiter. It tells us to look at Saturn's rings and moons as parts of a system, at Uranus and Neptune as field and wind machines, and at planets around other stars with the same system view. One flyby gave us decades of homework. Before Voyager, Saturn's rings were a bright band with one big gap you could see in a backyard telescope. After Voyager 1, the rings became a world in themselves. The cameras saw thousands of narrow lines, gaps and waves. Some gaps were made by tiny moons that live inside them. Their gravity clears the lane like a small boat's wake pushing away leaves. Some narrow rings keep sharp edges because 2 small moons, one inside and one outside, pull on them in a way that keeps the ring tight. These are called shepherd moons because they keep the flock together. Sunlight and shadow also matter. When the sun was low on the rings, small ripples cast long lines of shade. Those shadows showed that waves and ring edges have heights measured in tens of meters, even though the rings are wide in the other direction. In backlight, the rings glow with fine dust. In frontlight, they flash with bigger ice chips. That told us the mix of grain sizes and how light interacts with them. The radio science team sent a radio signal from Earth through the rings to Voyager and back. The way the signal dimmed told how thick each part of the rings was and how the grains were spread. The polarimeter read the light from the rings and told us grain shape and roughness. The magnetometer felt the ring plane as a place where the planet's field and the charged dust danced together. We also learned that rings are not fixed forever. They are stirred by moon pulls, by meteoroid hits, by the planet's own field, and by the slow spread of grains that bump and share energy. We saw faint rings beyond the bright ones. We saw spokes, dark streaks that cross the rings and change quickly. Spokes are dust lifted a bit above the ring plane by electric effects and light. We saw moons with odd shapes and surfaces. Bright Enceladus looked too clean, as if fresh ice had covered old scars. Mimas wore a huge crater. Tethys and Dione showed long, clean cuts and cliffs. Rhea looked soft grey and old. Titan refused pictures of its ground but gave us its air. Thick nitrogen and methane, cold and hazy. Saturn's air and rings also made waves and wobbles in each other. The whole system looked alive, not because it thinks, but because many small pulls and pushes make constant change. That is the key lesson. When you see a line of ice and dust around a planet, think of a slow river that carries news from every moon and moonlet, from every bit of dust hit by light, from every electric field line that hums through it. Voyager 1 did not stay long, but it taught us how to look, and that let later missions go deeper. Even now, when we see a thin arc around a small world, or a ring around a far planet around another star, we remember how the first close ring pictures showed a system where gravity writes patterns you can read. After Saturn and Titan, Voyager 1 took a new path. Titan's gravity bent it up out of the flat plane where the planets orbit. There were no more planned planet flybys. The cameras had done their big jobs at Jupiter and Saturn. Power would be tighter each year as the RTGs faded a little. Heat would be tighter too. The plan shifted from taking pictures to feeling space. Step by step, the team turned off heaters for parts that could stand the cold. They kept the big dish warm enough to stay the right shape. They kept the radio and the core computer alive. They kept the plasma wave, magnetometer, and particle tools running because those could read the sun's reach and the gradual change from solar space to star space. There was a quiet gift left in the cameras first. Before turning them off for good, the team used Voyager 1 in 1990 to take a family portrait of the planets. It turned its camera back toward home and snapped frames of the inner system. One small dot in a sunbeam was Earth. That tiny speck is the pale blue dot, a picture now famous because it shows our whole world as a point. The dot sits in a ray of light scattered in the camera by the sun, which is just off frame. The image is simple. A pinhead in a band of colour. Its meaning is large. It reminds us that all we know and love, every story we tell, every life, sits on a small spot in a vast dark. So after that picture, the cameras were shut down. The tape recorder stayed, the radio stayed, the pointing stayed, but the eyes closed. From then on, Voyager 1 became a listener and a feeler, a probe of fields and particles, a recorder of the sun's boundary. It watched cosmic rays rise as the sun's protection thinned. It listened for the hiss of plasma waves. It felt the magnetic field turn and smooth as it left the place where the sun's wind rules and entered the place where the galaxy's flow does. It measured shocks from big solar storms that took more than a year to reach it, long after we had seen the flares on the sun. It marked how the pressure outside pushed on the bubble of our sun's wind. The mission timeline changed too. No more quick days with thousands of pictures. Now there were long, calm months with steady data. The Deep Space Network scheduled long listening times with its biggest dishes because the signal grew weaker as the distance grew. Engineers nursed old parts. Thrusters had to keep the big dish pointed at Earth, but each tiny puff spent fuel we could never replace. The team made new software to use fuel more slowly. They changed heater plans to share warmth. They turned a few things off for good when power fell below what the whole set could support. Each change was like closing a room in a house in winter to keep the main room warm. The craft, now far past the orbits of the giant planets, kept going. Ahead lay the outer edge of the sun's wind, a place with a soft wall where the outward flow slows and the pressure from outside space begins to win. Beyond that, the true space between stars. Voyager 1 was set to be our first touch there. Picture the sun not as a still lamp, but as a slow, steady fire that blows a very thin wind in all directions. That wind is made of charged particles, tiny bits called protons and electrons, flowing outward at hundreds of kilometers per second. The wind carries the sun's magnetic field with it, stretching and shaping it as it goes. This wind does not go on forever. It pushes against the thin gas between the stars, which is also a sea of charged particles threaded by the galaxy's own magnetic fields. Where the outward push of the sun's wind balances the inward pressure of the space between stars, you get a border region. The whole wind-blown bubble is called the heliosphere. Its inner edge is everywhere around us. Its outer skin is far away, shaped like a changing, lumpy shell. The shell is not a hard wall. It is a set of layers where speed, density, and magnetic fields all change. For most of its early life, Voyager 1 drifted inside this bubble, reading the wind and the sun's storms as they washed past. The craft's plasma instrument that measures bulk flow had fallen silent years after launch, but a related tool that listens to plasma waves still worked. That meant the craft could no longer read speed directly, yet it could still hear how dense the charged gas was when it rang like a bell after solar storms. The magnetometer kept feeling the direction and strength of the magnetic field, and particle detectors kept counting high-energy cosmic rays that come from far beyond our sun. Deep inside the bubble, cosmic rays are fewer because the sun's wind and field deflect them. As you move outward and the sun's protection weakens, cosmic rays creep upward. That slow rise is a hint you are approaching the edge. Over years, Voyager 1's detectors showed just that, a steady, gentle climb in the cosmic ray count. At the same time, it recorded shockwaves launched by big solar eruptions long after we saw those eruptions near the sun. Those shocks are like slow tsunamis in the charged gas. They took many months to reach the spacecraft, and when they did, they shook the local plasma and made it ring. By listening to the tone, the team could tell how dense the plasma was around the craft, the way the pitch of a whistle tells you the size of a bottle. Density climbed as Voyager 1 neared the edge, because the outer layer, where the sun's wind slows and piles up, is thicker. The magnetic field also grew stronger and smoother in certain bands of time, like entering a zone where lines are pressed together by opposing pressure. All of these signs said the craft was not just far away, it was in a transition. The bubble's weather changes with the solar cycle, so the exact shape and distance of the edge move, breathing in and out over years. That is why there is no single simple number for how far the edge sits. Instead, there are clues: rising cosmic rays, changes in particle directions, stronger magnetic fields, and plasma density that steps up. Voyager 1 wrote those clues down with calm patience. It did not rush. It could not rush. It simply kept its dish aimed, kept its clock steady, and let the space around it speak in numbers. The idea that our star sits inside a blown bubble and that we can feel that bubble's skin from a tiny craft launched by hand is still a quiet wonder. The sun has a shore, and a machine the size of a small car was sailing toward it. Before the sun's wind meets the true outside, it first reaches a place where its speed drops from supersonic to subsonic, which means slower than the speed at which pressure waves move in that thin gas. That change makes a kind of shock front, like the shock wave around a jet that breaks the sound barrier in air, except this shock sits in a near vacuum and is shaped by magnetic fields as much as by pressure. This place is called the termination shock. It is not a razor line. It is a broad, shifting region where the wind slows, heats up, and becomes more turbulent. Inside the shock, the solar wind rushes outward, fast and straight. Beyond it, in the layer called the heliopause, the wind is slower, hotter, and more chaotic as it struggles against the push from outside space. Voyager 1 did not carry its working bulk flow plasma meter, by the time it reached this area, but it still had eyes and ears that could read the change in other ways. The particle detectors saw a rise in the count of certain energetic ions that are born when neutral atoms from outside the heliosphere wander in, steal a charge, and then get picked up by the sun's field and sped along with the wind. These pickup ions grow more common and energetic near the shock. The magnetometer felt the field twist and jitter as flows tangled. The plasma wave instrument noted that strong solar shocks sent ripples into the region that took on a new tone as density climbed. You can think of the termination shock as the beginning of the sun's shore break, the place where straight, fast water from the deep collapses into froth under the pushback from the land. The exact distance of this shock depends on how strong the sun's wind is at the time and what the pressure outside is doing. During parts of the solar cycle, when the sun's output is stronger, the whole bubble can breathe outward. During lulls, the bubble can shrink a little. Voyager 1 crossed this shock and entered the heliosheath, and for the first time it sailed in the slow water beyond the breaking point. The data stream told of hotter, more tangled plasma around the craft. Energetic particles bounced around more, scattering off magnetic irregularities. Cosmic rays from the galaxy pressed in, but the sun's field still eased some of that pressure. The field strength jittered, yet on average crept upward as lines were pushed together. No picture could show this, because there is nothing to see with light. But the numbers drew the map. This was the first craft to read the shock from the inside out, not from theory or from hints at Earth, but from a direct feel. The shock's lesson is plain. Our star is not alone. It carves out a space for itself in a galaxy that pushes back, and at the fight line the wind slows and warms. A small probe built with 1970s parts and patient hands felt that line and kept going. Beyond the termination shock lies the heliosheath, the sun's vast outer jacket of slowed, heated wind. Here the outward flow is not a rush but a push. The wind squeezes against the pressure from interstellar space, which is the thin gas between stars threaded by the galaxy's magnetic field. The heliosheath is thick, rough, and alive with structure, though everything in it is whisper-thin by our standards. Voyager 1's detectors counted more energetic particles, not just from the sun, but also trapped and re-energized in this turbulent zone. The magnetometer showed that the field lines were draped and stretched, sometimes aligned in long runs, sometimes twisted like rope. The plasma wave instrument listened for the ringing that follows shocks, and for the hiss that tells you about density. Every now and then the sun belched a strong blast, what we feel near Earth as a major solar storm, and that blast would take many months to reach the distant craft. When it did, the heliosheath shuddered. Plasma density jumped. The whole area hummed at a higher pitch. Those events, though rare at that distance, gave the team a way to probe the local gas. The pace of change was slow. Weeks and months were the time units now, not minutes. The flow was not even, because the bubble's outer pressure is not even. The galaxy's magnetic field pushes harder from some directions than others, and clouds of interstellar gas have patches that differ in density. The sun's output also varies by an 11-year cycle and by larger trends. Add all that up and you get a sheath that swells and shrinks, wrinkles and smooths, like a lung breathing and a flag in a shifting wind. As Voyager 1 climbed beyond the plane of the planets, it sampled a path that was not the same one Voyager 2 would later take farther south. Comparing the two paths taught us that the sheath is not a clean onion layer. It is irregular, with pockets and tongues. It is important to say that the plasma instrument that measures bulk flow on Voyager 1 had failed long earlier, so there was debate about exactly where each boundary sat. People used magnetic data, particle directions, and plasma wave tones to triangulate. That is science at its most patient, letting several small clues, none perfect alone, point to a shared answer. The main trend was clear. Cosmic rays from the galaxy kept rising. The sun's own charged particles changed in direction and number. The magnetic field grew stronger and more ordered at times. Density climbed in steps during shocks. All signs said the craft was pressing on the outer skin of our star's realm. The helio sheath taught us that the sun's bubble is not a thin soap film. It is a thick cushion that softens the blow of the outside for everything inside, including Earth. It taught us that the outside is close enough to touch with a human-made tool. And it taught us, again, that time and patience can turn a faint radio whisper into a map of a border no eye can see. The final skin of the sun's bubble is called the heliopause. Inside it, the sun's wind still sets the flow, even if slow. Outside it, the galaxy's medium rules. Crossing this skin is not like crossing a wall. It is more like walking from surf into dry sand, where the water no longer moves your ankles. The signs of crossing are a set of changes that happen together. The count of galactic cosmic rays steps up and stays high. The number of lower energy particles that stream out from the sun drops and stays low. The magnetic field strength changes and its direction shifts toward the steady field of the local interstellar space. Though at first, the direction can be confusing because fields drape and fold at the boundary. Plasma density takes a big step up, not because the galaxy is dense, but because the sun's wind there is slow and hot, while outside, the local gas is cooler and denser in charged particles. Voyager 1's bulk flow plasma meter could not read speed, but its plasma wave instrument could hear density when a passing solar shock made the gas ring. In one period, a shock launched many months earlier slammed into the region around the craft. The instrument heard a higher tone than before, which meant the craft was in denser plasma than it had been in the Helios heath. At the same time, the cosmic ray detectors reported a sustained high count of very energetic particles from outside, while the sun's own lower energy particles dropped and stayed low. The magnetometer saw the field grow stronger and become more uniform than the churning inside, though the direction did not flip dramatically in a single moment the way some had pictured. That taught us that the local interstellar field and the sun's field are not at right angles there. They may run in similar directions where they touch and slide. Put those clues together and you get a clear story. Voyager 1 had stepped into interstellar space. It had not left the sun's gravity. It had not left the faint breeze of solar particles entirely, because some leak in both directions across the boundary. But by the best definitions, it had left the solar wind's domain and entered the space between stars, becoming the first human-made object to do so. The distance was staggering and yet small in cosmic terms, far beyond Pluto, far beyond the planets, yet still only a tiny first step into the galaxy, like stepping across a yard while the journey to the next town is 1,000 miles. The crossing mattered for more than pride. It gave us a first sample of the outside weather that our whole heliosphere rides in, the pressure that sets the bubble's size, the field that can guide incoming cosmic rays, and the density that affects how our bow wakes move ahead of us. For decades we had drawn this border on diagrams. A small craft finally felt it. The day was quiet on Earth. There was no clap or flash. There was a line on a graph that rose and stayed risen, and a team of careful people who checked and checked again, and then allowed themselves a small breath of awe. We are in interstellar space. Beyond the heliopause, Voyager 1 became a weather station for the galaxy's edge. It counts galactic cosmic rays, which are high-energy particles from far-off blasts like supernovae. Those counts tell us about how the heliosphere shields everything inside from that radiation. When the counts go up because the sun is quiet and the bubble shrinks, we learn that people and instruments near Earth may face a slightly higher dose of space radiation. When counts dip after a strong cycle, we learn the bubble has puffed out and blocked a bit more. The magnetometer reads the interstellar magnetic field, which is weak but steady compared to the churning inside. Its direction tells us how the field lines wrap around our bubble and how cosmic rays might ride those lines toward or away from us. The plasma wave instrument listens for tones that ring when shocks and pressure waves arrive from the sun, even out here. Those tones are like ping tests that reveal local density and how it changes with time. The low-energy charged particle detectors watch for strange populations that mix across the boundary, like solar particles that leak outward and get turned around, or interstellar pickup ions that sneak in. Dust impacts, though rare, add to our knowledge of how grains drift in the local cloud around the sun. All of this happens at a whisper. The signal from Voyager 1 reaches Earth as a tiny trickle that our largest dishes must collect over long minutes to hours. Yet from that trickle we can track long-period waves, year-scale pulses, and slow trends that tell us about our galactic neighborhood. This is not space with bright pictures. It is space as touch and sound, felt through fields and particles. Why does it matter? First, it answers a basic question. What is our environment beyond the planets? We live inside a shield. It is good to know how strong that shield is and how it changes. Second, it connects small to large. The same physics that shapes our heliosphere shapes the bubbles around other stars, and those bubbles can affect how their planets are bathed in radiation and dust. Third, it teaches us how to design future missions that will swim in this sea on purpose, with tools tuned to its faint currents. And there is a fourth, quieter reason. Voyager 1 carries our patience to a place no one could visit any other way. It is a single point that moves outward and keeps a log. When a big solar event happens near the sun, scientists mark the day, then wait a year or more for the shock to reach Voyager 1. When it arrives, they can measure how much the interstellar plasma compressed, how the field turned, how the local cosmic rays changed. The long wait is part of the education. It slows our thinking to the pace of the outer dark. A radio reply from the craft takes almost a day in each direction. A storm takes a year to arrive. A change in the sun's cycle takes many years to shape the bubble. Voyager 1 is our metronome for that timescale. It reminds us that not all learning fits inside a news cycle. Some of the best learning comes from a small, steady ear listening in a very quiet place, writing down what the universe whispers. Voyager 1 speaks very softly. Its radio is not powerful. The dish on the spacecraft is big for a small craft, but tiny compared to the distance. By the time a signal reaches Earth, it is weaker than the heat from a candle on the moon. To make that whisper heard, 3 stations on our planet take turns listening. 1 in California, 1 in Spain, 1 in Australia. Together they are called the Deep Space Network. Each site has huge radio dishes as wide as a sports field. When Voyager 1 is low on the horizon for one station, it is high for another, so there is always at least one ear turned its way. The craft must keep its own dish aimed at Earth to within a tiny fraction of a degree. A small error wastes the signal into dark space. To hold that aim, Voyager 1 watches stars with a sensor, compares what it sees to a small sky map in its memory, and then makes tiny puffs with thrusters to nudge its body back into line. Every puff costs fuel, so the team wrote new ways to point that use fewer puffs, letting the craft drift a bit longer between corrections. The radio signal itself carries data using patterns that help the Earth receivers pull bits out of noise. Think of it like speaking in a rhythm that the listener expects, so even when a gust of static blows through, they can still guess the missing word. This is error correction. It adds extra bits that let the ground computer repair small mistakes. The receiver also stretches listening time. If a picture takes hours to send, that is fine. The craft stores measurements on a tape recorder and plays them back slowly. Over time, Earth gathers enough of the faint drip to rebuild the whole file. The speed of data is not fixed. When the Earth points a single big dish, the rate can be very slow. When several dishes are linked, or when we catch a pass during good weather with clean skies and low radio noise, the team may raise the rate a bit. Everything depends on how weak the signal has become and how much the antennas can collect. Light time delay is another quiet rule. At Voyager 1's distance, a radio message takes almost a day to reach it. A reply takes almost a day to return. That means no joystick control. Commands are written like sheet music, tested on simulators on Earth, checked by many eyes, and then sent in batches. The craft steps through them like a careful dance, and later the team reads the dance log when the radio trickle comes back. When a solar storm blasts out, it can make static even on Earth. It can also push the heliosphere's edge and change the plasma around Voyager. The receivers must hold steady through that. Engineers learn to spot when the noise is on Earth and when it is out by the craft, because both leave different fingerprints in the data. In deep winter at a ground station, heavy rain or snow can lower the quality of the link. Then the network shares time to keep the most important passes on the clearest dishes. All of this is quiet teamwork across oceans and years. A small craft half a light day away, a handful of giant ears on 3 continents, and a long line of people who plan, code, schedule, test, and watch. The result is a narrow thread that never snaps, carrying plasma tones, field lines, particle counts, and a calm report from a place no person has stood. When you hear that Voyager sent a new reading, remember that a weak whisper crossed a huge dark, found a dish on a small spinning world, and was pieced together bit by patient hands. Voyager 1 was built to last years, not half a lifetime, yet it still works because the craft and the team learned to live with less. Power comes from 3 nuclear generators that turn heat into electricity. Each year they make a little less. The team planned for that. They keep a power budget like a family that must pay heat, food, and rent from a shrinking paycheck. The always-on items are the radio, the brain, the pointing sensors, and a set of science tools that matter most out in interstellar space. Items that are no longer needed are turned off for good, like cameras after the last family portrait. Heaters are shuffled. Warm pieces share heat with cold neighbors through metal struts. On some parts, the team accepted colder limits than at launch, after tests on Earth showed they could survive. Fuel is its own clock. Every pointing correction uses a drop of hydrazine. There is no way to fill the tank, so the team changed how the craft aims. Instead of keeping a tight lock at all times, it now makes fewer, larger corrections and lets the aim drift a tiny bit in between, because the big dish has a small tolerance cone where the signal is still good. Software updates sent long after launch taught the craft new tricks with the same old hardware. That is like teaching a classic car to drive with finer gas savings without changing the engine. Old parts get sticky. Thruster valves can take longer to respond. The tape recorder can stall if handled too often. Sensors can drift in their calibration. The team builds new command patterns to coax sticky parts gently, warms a valve a little longer before a maneuver, or lowers the number of starts and stops on the tape drive. Safe mode is the craft's way to protect itself when it feels something wrong. It turns toward the sun or Earth, shuts down non-critical tools, and waits for help. At Voyager 1's distance, even that wait is long because messages crawl at light speed. Engineers keep drills fresh. They rehearse on a twin testbed on Earth with spare parts from the same era. They try fixes there first, then send them outward. Memory is tiny by our standards. The computer stores only a small set of steps, so the team writes clean timelines and sends them well ahead. If a storm on Earth delays a pass, the craft can keep working without new orders for a while. Heat cycles are slow. A sunrise on a solar-powered craft happens every 90 minutes in Earth orbit, but out here there are no orbits and no dawns. The craft sits in deep cold with steady, low heat from its own body. Metals shrink at low temperatures. Wires stiffen. Lubricants that would freeze on Earth are not used. Parts are dry or use solid lubricants. The box survived the years because it was built simple and because people on the ground kept learning how it aged. There is a gentle pride in making old gear do new things. It proves that careful work beats fashion and that good design lasts. When we say Voyager 1 still speaks, what we mean is that a web of choices keeps it alive each day. Which heater, which tool, which tiny puff, which listening window, which fixes for a small drift. Age is not a reason to stop. It is a reason to work more wisely. Even in interstellar space, the Sun still reaches Voyager 1, not with light that warms, but with changes that push the charged gas. A big solar eruption near the Sun launches a wave into the solar wind. Near Earth, we see the flare and the fast stream in hours or days. Out beyond the planets, that same wave takes many months to run down the long, thin river of plasma. When it arrives at Voyager 1, it compresses the local gas. Compressed plasma rings at a higher pitch. The plasma wave instrument hears that tone, the way a bottle sings a higher note when you blow across it after filling it with more water. From the pitch, the team can calculate the density. By collecting these events over years, they map how density changes outside the heliopause. They also see steps. After the crossing into interstellar space, there were times when the local density jumped and stayed higher. That told us that Voyager 1 had entered regions where the outside gas presses harder, or where the Sun's earlier storms had piled material against the boundary like waves stacking driftwood on a shore. The magnetic field readings add detail. When the plasma jumps, the field often grows stronger and steadier for a while. The cosmic ray detectors also register small dips and rises as their paths bend a bit more or less in the stronger or weaker field. Each late arriving wave from the Sun is a free probe. We did not need to carry our own hammer to knock on the wall. The Sun does it for us. The time gap also lets scientists test their models. They watch the Sun's surface, track a major blast, and then run computer models that predict how long the wave should take to reach different distances. When Voyager's tones finally arrive, they check the result. If the tone comes earlier or later, they tune the model. This teaches us the texture of the medium between the heliopause and the next small cloud the Sun is moving through. Some days, the count of galactic cosmic rays also shows slow, long ripples. Those may be tied to the 11-year solar cycle that pumps the bubble larger and smaller. Even beyond the edge, the memory of that breathing carries on. The craft does not see pictures of these changes. It feels them on its skin as pressure and on its ears as tones. When people say Voyager 1 heard the interstellar plasma sing, they mean these rising whistles when a wave passes. That sound never reaches human ears directly. It is a voltage trace that engineers scale to audio so we can hear what the instrument recorded. The beauty of that translation is not only art, it is a way for our brain to grasp how a place we cannot touch behaves. A higher note means more crowded charges. A lower note means thinner gas. Over years, the tune climbs with small leaps. It is proof that the craft is not floating in a still void. It is sailing in a thin, slow stream that changes with the Sun's heartbeat and with the soft pressure of the galaxy around us. Life on Earth grew under a shield. The heliosphere keeps some of the hardest radiation at bay. When Voyager 1 tells us how strong that shield is, it helps us understand the background risk for people and machines beyond our air. Astronauts traveling far from Earth will care deeply about how many high-energy particles pierce their ship and their skin. Electronics on long missions will care too, because cosmic rays can flip bits and wear parts. The count that Voyager sends is like a space weather report from our border. It also helps us understand other stars. Every sun blows its own bubble. Some are weak, some are strong, some plough through thicker parts of the galaxy, some through thinner. A planet sitting inside a tight, strong bubble may face fewer cosmic rays. A planet sitting near a star with a weak wind or moving through a harsh patch may face more. That background can affect clouds, air chemistry, and even how often life sees the kind of damage that can break DNA. We do not claim a simple line from cosmic rays to life, but we do know that radiation shapes the stage life stands on. Voyager's numbers add real local data to that big question. The mission also teaches us how to build probes that last and what they should carry to read a faint sea. A future interstellar probe, launched on purpose to sample the local cloud and the next one beyond, will pack better plasma meters, more precise magnetometers, and radios even more sensitive than today. It will know from Voyager how to pace itself, what to expect, and how to work with our ground network. Finally, there is the cultural part. We are a species that tells stories about borders. The first humans looked past a hill and wondered what was on the other side. Voyager 1 crossed a border that is real and yet invisible, and then kept going. It turned a diagram in a book into a measured place with numbers, dates, and tones. That changes how children draw the solar system in their mind. It is no longer just circles of planets around a sun. It is a sun inside a moving bubble with a wrinkled skin pressed by the galaxy's field, breathing with the solar cycle, and carrying a small scout at its edge. From a practical view, this helps protect future explorers. From a human view, it reminds us that our home has a shore. Shores make us careful and humble. They also make us curious. Beyond this shore lies a long, empty reach dotted with faint clouds. One day we will send a craft fast enough to map those clouds in a single human career. When that day comes, the flight plan will start with a quiet nod to a probe that flew slowly, spoke softly, and taught us where the water starts to taste like the wider sea. What Voyager 1 sends home does not live only in news pages. It lives in archives, where any student years from now can fetch the raw counts and make their own graphs. The tape recorder on the craft plays back to Earth, and then those bits are stored in careful systems with backups across places. The images of Jupiter and Saturn were cleaned and stacked to make the sharp mosaics you know. The magnetic field lines and plasma tones are kept with times and settings so that later teams can test new ideas against old data. This long memory matters. When we learned more about rings from later missions, people went back to Voyager pictures and found details they had missed. When we learned more about plasma waves, people listened again to old tones and heard new notes. The craft also carries a different kind of memory outward, the golden record. It is a time seed, saying here is how we sounded, looked and lived when we first reached beyond the planets. No one expects a finder soon. Space is huge, but the record will last as the craft drifts for millions of years unless a small rock strikes it. In that way, the name Voyager truly fits. It is a traveler and a messenger, and the message is as much for us as for any stranger. We chose to send a kiss, a baby's cry, and rain on leaves. We chose to send greetings in many tongues, not one. We drew simple tools and complex bodies. We put math and music side by side. That choice says we are not only builders, we are also sharers. Back on Earth, the name Voyager sits in classrooms, on posters, and in the voice of a person who looks at the pale blue dot and feels smaller and kinder. The mission changed careers and lives. Students who saw the first volcano on Io now teach new students who study ocean worlds. Children who fell asleep to the picture of Saturn's rings now build instruments for the next probe. A small machine launched in 1977 still shapes people who were not born then. There is another memory too, in the way we work. The Deep Space Network learned to link dishes, to pull bits from nothing, to schedule across continents. Teams learned to fix old code, to rewrite timelines on the fly, to operate a craft beyond its design life. Those skills help many other missions. They are Voyager's quiet legacy in our hands, not just in the sky. If you step back even farther, you can see a story of us learning to think in longer time. A note sent today gets an answer tomorrow. A wave on the sun makes a tone at the edge next year. A field trend takes years to show. Voyager 1 trained us to breathe in that slow rhythm. In a world that often moves too fast, a patient rhythm may be the most precious gift a machine can bring home. Hold a simple picture. A dark room, a small speaker, a faint hiss that slowly reveals a pattern, a rise, a fall, a steady line. That is Voyager 1 now. No camera clicks, no bright close flybys, just a steady ear and a warm heart on the edge of the sun's reach, counting particles, feeling fields, and sending home what it learns. It began as a hurried child of a rare alignment, flung outward to visit two giants. It showed us Jupiter as a living storm world with a ring and a moon that breathes fire. It showed us Saturn as a ring system of lace held together by gravity and lightning and dust, and a big moon wrapped in orange air. It turned and took the family portrait that held our world as a tiny light in a sunbeam. Then it put away its eyes, pointed its dish, and walked on. It found the sun's shore, felt the slow break of the wind, and crossed into interstellar space, the first human-made thing to do so. Since then, it has been our border post. When the sun coughs, it hears the shock a year later and tells us how the outside gas rings. When the galactic field presses harder, it feels the lines tighten. When cosmic rays rise, it counts. It does all this on a few hundredths of the power of a kettle, warmed by the steady fade of small cores that glow in the dark. It is old and careful. Each heater is a choice. Each puff is a choice. Each pass on a big dish is a choice. Behind every choice is a person at a console, a schedule on a wall, and a chain of hands that began work before some of us were born. We do not know how long it will last. One day a valve will stick for the last time, or a heater will fail to keep a line above the cold, or the radio will fade into the noise. When that day comes, the craft will keep moving anyway. It will pass other stars in long ages. The record on its side will keep its stories of rain and heartbeats. In a far future, a dust of human copper may cross a place no one can name. For now, while it still speaks, we can be grateful. Voyager 1 makes the solar system feel complete. It gave our sun a shore you can point to, measured by a small ship with a white dish and a calm voice. If your eyes are heavy now, let that voice fade to a soft hum. Picture a tiny craft against a starfield, the sun a bright point behind it. Think of a line of patient people sharing night shifts to keep the link. Think of a record with music in the dark. Think of a small dot in a sunbeam. We live on that dot. We built the ship. We learned from the road. Thank you for coming along. Sleep well and good night.